Hi everyone, welcome to Physics 2001, Section 102, Lecture 18. This is the second lecture on rotational motion, and the last one on rotational motion. Before we get started, I just want to go over a few organizational notes. So the first is please see the course webpage. If you click on this link, it's the course webpage. Please see that for the slides. You can also get video links. So either an MP4 download or a YouTube video link, and you can click on the Google Docs link where there are question and answer for a given lecture. Please do email me any questions about this lecture, and I will post the answer, the question without your name. I'll post the question and the answer in that Google Doc for this lecture, and I'll do that for each lecture. So again, go to the course webpage for that information. I hope you're all doing well, you and your families. If you have any issues with completing any of the work on time or taking the exam at the time we'd like to do it, any issues at all, please let me know and we can work on some accommodations. Okay, I really want to be flexible here. I realize these are suboptimal conditions. So pursuant to that, the midterm 2 will take place on Monday evening on lon-capa, so that's Monday of next week. We will have a practice exam posted by the end of the week is the plan, and the idea, though more instructions will go out, is that on Monday evening, on March 30th, the exam will be open for several hours, so you could start it within a many-hour time window, but once you start it, you'll have 90 minutes to complete it. So you need to make sure you have kind of a continuous internet connection, and we have some contingencies planned for if your internet connection does fizzle out on you, so please look forward to announcements for that. Other organizational notes, office hours, let's just do that via email. I don't think it's going to be practical or useful to have a fixed office hour time, so email me. I can try to answer your question via email, or we can try to set up a time to do a video chat via Microsoft Teams. You've all received an invitation to Microsoft Teams, so please download the app on your browser or phone or tablet or whatever it is that you do, and you can use that. We're not going to mostly use it for the class, but if we do have to video call, it's probably the best way for us to go about doing that. Similarly with Teams, Emma, the SI instructor, she's going to be running her SI sessions through Teams, so please consider going to those. The plan is that the help room TAs will also be populating Teams at the regular time from 6 to 9 p.m. on Wednesday and Thursday. I'm also going to ask them to answer your questions via email. I'll send out more instructions for that in the future. If you want to sit through a live lecture for whatever reason, then you, I believe, have been added as well to the morning section Teams, and you can watch Dick Picard's lectures if that's the kind of thing that you want to do. And then note the homework and the pre-class assignments are pretty much as they were before. So just keep on doing what you were doing there. Okay, so let's just jump into a question, sort of going over stuff we learned last time. So consider two masses on a rod that's rotating. So this is as shown below. So in case A, we have masses at the end of the rod here. In case B, the masses are closer to the center, but it's the same masses. So basically, going from A to B, we've just taken those end masses and shifted them inward. Okay, so if we apply the same torque, let's say out at some distance, we apply a force at some distance, the same torque in each situation, which arrangement of masses is going to have the lowest angular acceleration? Is it going to be A, B, or are they going to be the same? So take a moment and think about it. Probably should pause the video. I'm going to assume that you've paused and you've come back. And it's going to be A is going to have the lowest angular acceleration. So why is that? Remember that just like F equals ma, tau is equal to I alpha. So the torque is equal to the moment of inertia times the angular acceleration. Torque is also equal to the force applied at some distance from the axis of rotation. but it's the perpendicular force that we're concerned with, so that's why there's the sine theta. And that's going to be the same for both. That's what we defined in the question. So then we do some algebra here, and that means that the angular acceleration is the torque divided by the moment of inertia, but the torque is the same for both. So then mass A, right? Remember mass A, its mass is, case A, its mass is not as concentrated towards the center, it's further out. So it's going to have a larger moment of inertia, meaning a larger denominator, and therefore a smaller fraction overall, so smaller angular acceleration. So then case A is going to have the lowest angular acceleration. Okay, let's do a sort of related follow-up question. So we're going to consider two masses on a rod that's attached to an axle rotating as shown. So now the two masses at the end of the rod are placed identically in each situation. In each rod, which it's a massless rod, it's turned by pulling a string wrapped around the center of an axle, which is also massless. Okay, so just what we have here is the masses at the end are the same, the rod is massless, and the axle, which is the circle here, is massless. That's true in both cases. So what we've done is we've now, though, applied a force from the axle. It's the same force in cases A and B, but note that in A, the force is closer to the axis of rotation. In B, it's further from the axis of rotation. So if the force is the same in both cases, which one, A or B, is going to have the smallest angular acceleration? It's going to be A, B, or are they both going to have the same angular acceleration? So as usual, pause the video and think about it. I'm going to assume that you've paused it and come back. And A is going to have the smallest angular acceleration. So again, remember that tau is I alpha, torque is moment of inertia times angular acceleration. Torque is also force applied at some distance, but we're concerned with perpendicular force, so we have a sine theta factor there. And then we can do some algebra. Alpha is then equal to tau over I. In this case, the masses are distributed identically, right? So we have masses at the end of the rod, they're identical, and in both cases, the rod and the axle are massless. So these two are going to have the same moment of inertia, but in case A, the force is applied at a smaller distance from the axis of rotation. In B, it's a larger distance, and therefore the torque overall is going to be larger in case B. So that torque is smaller in case A. You have a smaller numerator in your fraction, and therefore you have a smaller angular acceleration. Okay, so now let's look at a sort of complicated situation. It is complicated, and there's lots of questions you could ask about this, but this is good practice at focusing on what's relevant. We're not going to solve this whole problem all in one go. So what we have here is a T-shaped rotating post. Okay, so this post here can rotate. And we have mass M, identical masses M, hung from the end of the T on the post. So these are positioned at distance r from the rotation axis. We have a string wrapped around the base of the post. It runs through a pulley, and it's wrapped through a hanging mass M. Okay, so sorry, this mass is pulling from the pulley there, and that is going to pull the string. That's going to unravel from the post. It's basically going to cause the post to rotate. So for instance, we could solve what happens in this scenario. How quickly does this thing begin rotating, for instance? But the question that we want to focus on now is, what is the total moment of inertia of the post and the masses at the end of the post? Okay. So let's take a moment and think about it. You probably want to pause the video. Note that equations down here, we have the moment of inertia for a cylinder and for a point mass. And these guys, because they're far from the axis of rotation, we can put them as point masses. So I'm going to assume that you've paused it and worked on this, and you'll find that it's C. So 0.5 kilograms meters squared is the total moment of inertia of the cylinder plus the masses. So why is that? So remember that if you have a multi-component object, so that means there's multiple components that are kind of pieced together, then the total moment of inertia is just the sum of the moments of inertia of the individual components. So here we have a cylinder and we have 2 point masses. So then the total moment of inertia is just the addition of cylinder plus point mass 1 plus point mass 2. So the cylinder is given in the bottom right hand slide, that's 1/2 mr squared. Here r is the radius of the cylinder and m is the mass of the cylinder. And then for the point masses, they happen to have the same mass m in this problem, but they're located at a distance capital R from the rotation axis. Okay, so then we can just plug in our numbers. Again, the post and the masses in this case both happen to weigh 1 kilogram. Post has a radius of 0.1 meters, and the masses themselves are 0.5 meters from the axis of rotation. So you plug all those numbers in, and you find that it's 0.5 kilograms meters squared. So now let's introduce a new quantity, angular momentum. So we did mention this in last lecture, but we didn't really use it. So you'll remember that last lecture we established that there's this beautiful relationship between linear quantities in terms of kinematics and dynamics equations. This is beautiful correlation between these linear quantities and a rotational quantity. So for instance, we can map between length and angle, velocity and angular velocity, mass and moment of inertia, torque and force. And we mentioned that we had linear momentum in our collisions that we went over, but now for rotation, there's also a thing called angular momentum. So again, what we do is we take our linear equation and we plug in the rotational quantities. So linear momentum, this is mass times velocity. So remember, in the rotational space, mass is moment of inertia, right? These two correspond to each other. And velocity is angular velocity, right? So then we plug in I and omega here, and that gives us this equation. The angular momentum is the moment of inertia times the angular velocity, okay? Now, why do we bother defining this? Is just as the linear momentum is conserved in the absence of an external force, the angular momentum is conserved in the absence of an external torque. So if something is rotating and there is no external force being applied to it, then that angular momentum will stay the same. It's conserved. And that's going to be very convenient for solving some problems and understanding some physical scenarios. So this is a new equation. You need to know that L is equal to I omega. So capital L is what we use for the angular momentum, and that is equal to the moment of inertia times the angular velocity. So again, it's conserved, and so if I have some scenario, so some object that's rotating, and then let's say, for instance, I change the distribution of the masses on that object, but I haven't applied any external forces, then my final angular momentum will be the same. Okay, so something else will have to change in order to maintain that, that constant angular momentum, and we'll see some examples in a moment. So if we just expand our equations, that means that the initial moment of inertia times the initial angular velocity is equal to the final moment of inertia times the final angular velocity. Okay, so for instance, if I shift my masses around, then I get a different final moment of inertia, and that means that the final angular velocity is going to have to adjust to compensate for that in order to maintain a constant angular momentum. So this angular momentum, one thing I want to point out, this is a vector, and the direction corresponds to the so-called spin axis. So for instance, if I have an object that's rotating around a circle as indicated by the circle with arrow marks on it, something that's going around in a circle, then the angular momentum vector is going to be pointed in the direction of the thumb here. Okay, so it is perpendicular to the plane of the orbit. And if you want to figure out whether you're pointed up or down, then you do something called the right-hand rule. You curl your fingers around in the direction of that circular motion or in that rotational motion. So you take, for instance, your index and middle finger and ring finger and pinky, and you curl those around in the direction of rotation, and then your thumb is going to be pointed in the direction of the angular momentum vector. So that is the right-hand rule, and it's used for lots of other scenarios in physics. So why do we care about angular momentum? There are a couple of very interesting consequences for angular momentum conservation. So one of these is that a spinning object is going to keep pointing in the same direction. That's because angular momentum is a vector. That vector is conserved, and so it's going to keep pointing in the same direction unless an external force is applied. So if you have a spinning object and you want to change its direction, how it's tilted or how it's pointed, then you need an external force, which is an external torque, to do that. So a spinning object is going to tend to stay pointed in the way it was originally pointed. So for instance, this is why why rifles have rifling. Okay, so if you're going to fire a bullet from a rifle, you'll notice that if you look down the barrel, which if you ever do this at home, make sure that your gun is not loaded. You shouldn't even have the magazine attached to the gun. So please don't look down the barrel of a gun. But if you were to ever look down the barrel of a gun when it is not loaded and you're 100% sure it's not loaded, then you'll notice that there are these spirals. And this is known as rifling. And what that does is when the bullet is fired, it basically begins to spin because of the rifling. And as the bullet is flying through the air, it is executing a spiral. Okay, similarly, when you throw a football, the reason when you throw a football and you try to make it spiral is for the same reason that this bullet here has rifling. So once these objects here are spinning, then their angular momentum vector is going to be pointed in the direction that they're moving, right? Because they're rotating. The plane of rotation is perpendicular to the direction of motion. And so the angular momentum vector is going to be pointed perpendicular to that plane. And these objects then are going to tend to continue moving in that way. So they won't tumble. Basically, if these objects start to tumble, then there's going to be more air resistance, and that's a problem. So that's why you have rifling and why you throw a spiral. Now, why do these eventually begin to tumble anyways? I mean, you can try that, throw a football, the flight path won't be exactly perfect. The spiral will start to deteriorate if you don't spin it hard enough. And that's because you do have an external torque, right? You have gravity. So gravity is acting on these as a force, and that may or may not cause these things to rotate. Similarly with the top, the reason that the top continues to spin so nicely is that you have this thing is rotating. The angular momentum vector is oriented perpendicular to that rotation, and that is conserved, and so that top will continue to spin until finally gravity and then friction from the point of the top on the surface finally begins to affect the motion. And because these are external torques that are being applied to your object. One more example is a bicycle. So for those of you that are able to ride a bicycle with no hands, the reason that you can do that is that when your bike tires are rotating, they have quite a bit of angular momentum. And that angular momentum vector is pointed, in this case, perpendicular to your direction of motion. Right? It's also perpendicular to the wheel. And yeah, that angular momentum is conserved, and so it's very difficult there's resistance to tipping the bike one way or the other, because that would, you're basically fighting that angular momentum conservation. Another consequence, one that's pretty interesting, is that if you have an object that's spinning and its mass distribution changes, that's going to change the rotation rate. Or if you change the rotation rate and you want to conserve angular momentum, you're going to have to change the mass distribution. So for instance, figure skaters, if someone's skating along and look, they're spinning rather slowly before they jump, and after they land, they're also spinning rather slowly. But in the air, this person's spinning very rapidly. So how do they do that? Well, they bring their arms and their legs inward, right? They tuck them in, and so they're moving their mass distribution closer to the rotation axis. And there's no external force when they're in the air. So if they move their mass distribution closer to the rotation axis, that means to conserve angular momentum, their rotation rate has to speed up. And that's in fact what happens. So that's how they spin faster and faster, is they just tuck their mass inward. An example that I am very fond of is from astrophysics, related to my research, is a thing called a pulsar. So when you have a massive star, something like, let's say, 10 times the mass of the sun, when it ultimately uses all the fuel in its core, the core will collapse. There's a big, beautiful explosion called a supernova, and this thing left behind called a neutron star. That's basically the mass of the sun, but compressed down to the size of a city. And these things are often rotating quite rapidly, so 60 to 60,000 RPM. And the way that they're rotating so rapidly is that you had a somewhat, let's say, reasonably rotating core of a star, but then when that core collapses, in order to conserve angular momentum, the leftover remnant, which was formerly the core, needs to be spinning much more rapidly in order to conserve angular momentum. So remember, angular momentum is L, that is equal to I omega, so moment of inertia times angular velocity. In both the figure skater case and the pulsar case, we've very much decreased the moment of inertia, and therefore we need to increase the angular velocity in order to conserve angular momentum. So let's do a practical question here. Let's put this into practice. So let's say we have a professor and they're sitting on a turntable and they're holding two 2-kilogram masses in their hands. So in each hand they have a 2-kilogram mass. And their arms are folded close to their body. They're on a turntable, so a rotating stool, and they're rotating. Okay. When they stretch their arms out with the masses in their hand, what is going to happen to their angular velocity? Is it going to increase, decrease, or will it stay the same? So take a moment to think about that, and I'm going to assume that you have thought about that. Pause the video, and you'll see that their angular velocity will decrease. Okay, so here's the example. They're rotating, they bring their arms in, they start to rotate faster, they put them out more slowly, and so there's no external forces here. All that is happening is they are changing their mass distribution, therefore changing their moment of inertia, and in order to conserve angular momentum, their angular velocity must increase to compensate if they bring the masses inward, or it must decrease to compensate if they move the masses outward. So again, angular momentum is conserved. This is what I was saying a moment ago, is that L equals I omega. This is constant. And you decrease I, you increase I by moving the masses out, and therefore you must decrease omega. Let's do a follow-up example here. So we have a turntable, that's the gray disk, and each red dot here represents a 1-kilogram mass attached to a massless turntable. The inner circle has a radius half that of the outer circle. If the masses start in configuration A and wind up moving to configuration B while the turntable is spinning, how does the final moment of inertia of the turntable compare to the initial? So there's no external torque. The masses have just, in the middle of rotation, gone from configuration A to configuration B. So how does the final moment of inertia compare to So take a moment and think about it. Pause the video. I'm going to assume that you're now back. And you'll see that the moment of inertia is now smaller because we've brought more of the mass inward. Right, so the mass is more concentrated towards the center, more concentrated towards the axis of rotation, and therefore the moment of inertia has decreased. Let's do a follow-up question now. So again, we have our masses go from configuration A to configuration B. The question here is, how does the final angular momentum of the turntable compare to the initial? So this object is spinning, and the mass is moved from A to B. What happens to the angular momentum? So I'm going to assume that you've paused it, thought about it, and answered. And you see that it's the same, right? There is key here. There is no external torque. Angular momentum is conserved in the absence of any external torques. So it needs to be the same. Okay, so another follow-up question that you probably saw coming. So again, we have turntable spinning. The masses are in configuration A. They move to configuration B while the object is spinning. Now we want to know, how does the final angular velocity of the turntable compare to the initial? So take a moment, think about it. I'm going to assume that you've paused the video and you've now come back. And of course, the final angular velocity must have increased. It must be greater in configuration B than A. So angular momentum is conserved in the absence of any external torques. And we've defined in the question there are no external torques here. And that means that if angular momentum is the same, then L is equals I omega, that is constant. We've established that because we move the masses inward for case B, they're more concentrated towards the center, then our moment of inertia has decreased, but the product of the moment of inertia and angular velocity has to stay the same. So if I decreases, then omega must increase in order to compensate and maintain that angular momentum, keep that conserved. And that the angular momentum is conserved in the absence of external torques. If you want, you can just think of this as a law of the universe. I mean, it really is. It's a fundamental principle. So it is conserved in the absence of external torques. So when we decrease that moment of inertia, we need to increase that angular velocity. In this scenario, okay, rotating, we're still rotating, but while in the middle of rotation, little motors have moved the masses inward to 0.25 meters. So the question is, what is the new angular momentum for this scenario? Take a moment and think about it. Pause. And you're back. And it's the same. It's 5 kilograms meters squared per second. We have not applied any external torque, so angular momentum is conserved. We found that it was 5 kilograms meters squared per second, and now it is still the same. Okay, so we've decreased our moment of inertia because the masses are now more concentrated towards the center. So what would happen here is those little motors would move the masses inward, and the whole system would start spinning more rapidly. But again, that's conserved, so it hasn't changed. So now, what is that new angular velocity? So we've established that the motors have moved the mass inward. That has decreased the moment of inertia. So the question is, what is the new angular speed? Because angular momentum is conserved. So I'm going to assume that you've paused the video and you've come back. And you find that 20 radians per second is the new angular velocity of this rotating object. So again, our moment of inertia or our angular momentum rather, is conserved. We found that it was 5 kilograms meters squared per second, and that is going to stay the same. That is equal to the initial moment of inertia times the initial angular velocity. it's going to be equal to the final moment of inertia times the final angular velocity. So we solved for the angular momentum, so we know what L sub F is, and we have enough information to obtain the new moment of inertia, this final moment of inertia. So we just have to solve for that, and then we'll extract our final angular velocity. So with some algebra, right, that final angular velocity is equal to the angular momentum divided by the final moment of inertia, and we can solve for that final moment of inertia. Then the new radius of the point mass is this 0.25 meters. We find that our final moment of inertia now is 0.25 kilograms meters squared, and we just do the rest of the arithmetic, and we find that 20 radians per second is our new angular velocity. So qualitatively, what's happened is the masses have moved inwards. That means the moment of inertia is smaller because mass is more concentrated towards the center. And then the whole system has to speed up in its rotation rate in order to compensate. So let's do another follow-up question here, or not a follow-up, but a related question, but this one's now just totally qualitative. So we have each red dot here representing a 1 kilogram mass on a massless turntable. The blue dot is 2 kilograms. So the blue dot has more mass than the red dot. The inner circle here has a radius that is half that of the outer circle. If the masses start in configuration A and move to configuration B while the turntable is spinning, how does the final angular speed of the turntable compare to the initial? So let's assume that there's no external torque, and keep in mind the mass equation is here for moment of inertia. And when you want to solve for the moment of inertia for system A, you need to add up the moments of inertia for the 3-point masses. Similarly for B. So I guess when I said this was qualitative, I lied. There's a quantitative bit. So basically, you're going to figure out the moment of inertia for A relative to B, and then you can determine has that increased, decreased, or stay the same, and that will inform whether or not the angular speed must have increased, decreased, or stayed the same. So I'm going to assume that you have paused the video and you have worked on this and come back. And you'll see that the angular speed is actually going to be the same. Okay, so how is that? Well, remember, angular momentum is conserved in the absence of an external torque, and we have, by fiat, said that there is no external torque. So the initial I omega, moment of inertia times angular velocity, is equal to the final I omega, final moment of inertia times final angular velocity. We can calculate the initial moment of inertia. We have 2 times the mass of the red one times that distance from the axis of rotation for the red one squared, plus same thing for the blue, but its mass and its distance. Now, to get more quantitative here, we can take into account that the radius from the axis of rotation for the blue mass in the initial situation, that's what the I means, is 1/2 of the radius for the red masses, and the blue mass is 2 times the red mass, right? It's 2 kilograms, the red's 1 kilogram. So then we can combine these, right? Because we'll substitute in the information about the red one into this equation for the blue one. And we find that the initial moment of inertia is 5/2 times the mass of the red object times the radius of the red object, the initial one squared. So that's our initial moment of inertia. Now for the final scenario, again, it's a multi-component object, so we will add the moments of inertia for the red objects to the blue object's moment of inertia. Now the red radius is 1/2 of the blue radius for the final scenario, and still the blue mass is twice the mass of the red object. So our final moment of inertia, we're going to plug in the information about the red guy into the blue guy, and we find that the final moment of inertia is 5/2 times the mass of the red one times the radius of the blue squared. But remember, the final blue position is equal to the initial red position, and therefore these two moments of inertia are equal to each other. And so the moment of inertia has not changed. So IF is equal to II, and there's no external torque. So the product of I omega has not changed, and therefore omega can't have changed. Okay. So the angular velocity here is going to be constant. We can take conservation of angular momentum and apply this to objects in a circular orbit or even an elliptical orbit. And we do elliptical here because it's a bit more interesting, a bit more fun. So angular momentum, this is conserved for any system in the absence of an external torque. Okay, any system at all. So this includes objects in elliptical orbits, like for instance, a planet in the solar system. So when the Earth goes around the sun, that's not an exactly circular orbit, it's slightly elliptical. Or if you have a satellite going around the Earth, that could also be in an elliptical orbit. It's not exactly a circular orbit. Okay, so in an elliptical orbit, the orbiting object, right, it's going to be moving further from and closer to the more massive object as it's orbiting. So what do I mean here? I mean, let's say we have an object going around the Earth, for instance. It's doing this path here. So perigee is when you're really close. Apogee is when you're far. So afar is apogee. It's kind of a way to try to remember it. And that's what your elliptical orbit is. So again, furthest distance is the apogee. The closest is called the perigee. And angular momentum is conserved here. If I have an object, for instance in this picture, orbiting the Earth, there's no external torque, so angular momentum is going to be conserved. It's the same at the apogee as it is at the perigee. And that angular momentum, recall, L is equal to I omega. So for our satellite, the moment of inertia, it's just going to be a point mass, so mass of the satellite times the radius, the distance from the center of the Earth, squared. But it's clear that the radius for apogee, is greater than the distance for perigee, right? So that means that the moment of inertia is larger at apogee than it is at perigee. But the angular momentum is conserved. And so therefore, if you have a larger moment of inertia here at apogee, you need to have a smaller angular velocity to compensate. And at perigee, the angular velocity is going to be faster. So this object is going to be moving quicker here, and then more slowly, and then quicker, and then more slowly. So the satellite basically moves faster as it approaches the object, and slower as it moves away. So one qualitative way, as I guess semi-quantitative way that this is described, is Johannes Kepler coined laws of motion, and one of them that he figured out a long time ago was the second law of planetary motion, and that is that planets sweep out equal areas in equal times. And so what we have here is, to conserve angular momentum, our planet is moving slower when it's further away from the object it's orbiting, because it has a larger moment of inertia. And when it's closer, the moment of inertia is smaller, so it's moving faster. But if you wanted, you could say for a given time window, how much area have you swept out? So you create a sort of triangle from the initial angle to the final angle in some elapsed time. And you do the same thing for the same amount of time, closer to the object, at for instance, perigee here. And these areas are going to be equal to each other. You don't really need to know this. This is just a consequence of angular momentum conservation. So as long as you know that L equals I omega, and that's constant in the absence of an external torque, then you basically already know the second law of planetary motion. Just as a fun fact, the terms perigee and apogee, these are general for really any object, any satellite orbiting any body. When you're talking about things going around the sun, this is called aphelion, and this is called perihelion. And this is aphelion with a PH, okay, and that's perihelion, just so you know. Now let's put that into practice. So angular momentum conservation for an elliptical orbit. So let's consider Halley's Comet. So Halley's Comet, this completes a full orbit of the sun every 75 years. So it's truly a once in a lifetime thing, or twice in a lifetime if you're really lucky and you were born in the right years. So at closest approach to the sun, which is perihelion, it's moving at 54 meters per second. And so that 54 meters per second at closest approach to the sun is something called 0.57 astronomical units. That's a distance that I'll explain in a moment. Now the question is, how fast is Halley's Comet moving when it's the furthest from the sun, when it's at aphelion, which is 35 astronomical units? So keep in mind for this problem, you don't really need to know what an astronomical unit is, right? It's just a distance. In case you're curious, it is an Earth to Sun distance. Okay, so we have Halley's Comet. It takes 75 years to make a full orbit, and when it is at the closest distance to the sun, it's moving at 54 meters per second. Right, that's pretty fast. It's like 100 miles an hour. Now, when it's all the way out at 35 astronomical units, so very far from the sun, how fast is it moving? You can get a qualitative answer by looking at the GIF here. The GIF gives you an idea, but quantitatively you can work this out. So again, keep in mind, what do you need to know? That this is a point mass. You have the moment of inertia for a point mass. And remember that the transverse velocity, or the tangential velocity, that's what you want here, this is equal to the distance from the orbiting distance times the angular velocity. Okay, so you can use angular momentum conservation to figure out what the angular velocity is at the two radii. You have the two radii, and therefore you can figure out what the transverse or tangential velocity is. So I'm going to assume that you've paused, worked on this, and that you've come back. And you'll see that it's 0.88 meters per second. So that's like a walking distance, or walking speed, when Halley's Comet is at its furthest distance from the sun. So it goes from basically a walking speed to pedal to the metal on your car speed. It's kind of neat. And quantitatively, how do we figure that out? Again, angular momentum is conserved, and so your moment of inertia at perihelion times the angular velocity at perihelion, this is the close part, is equal to the orbital angular momentum at aphelion, which is equal to the moment of inertia at aphelion times the angular velocity at aphelion. So this is the far part. And we can do a substitution here for the angular velocity. So remember, the transverse or tangential velocity is equal to the distance from the it's the orbiting distance times the angular velocity. So we can substitute in, if we divide basically this transverse velocity by the radius, then that is equal to the angular velocity. So we substitute that in, and we have some r's that cancel here, and then that is now our angular velocity, or sorry, our orbital angular momentum. And the angular momentum at aphelion is going to be the same equation, right? It's the mass of the comet, which is unchanged, but you now have a new distance and a new velocity. These have to be equal to each other. Angular momentum is conserved, And so we can set the initial angular momentum equal to the final. The masses cancel. We don't care what mass Halley's Comet is. So we have that the orbiting distance at aphelion times the transverse velocity at aphelion is equal to the orbital distance at perihelion times the transverse velocity at perihelion. And then we just do some algebra to figure out what that velocity, that transverse velocity, is at aphelion. We do that algebra and then plug in our numbers. And here's where the astronomical unit cancels, you see, so you don't need to know what the Earth to Sun distance is. You just need to know the relative distances. And you see 0.88 meters per second, which is kind of cool. So the last thing that I want to go over here is just a preview for what we're about to cover. So the next lecture is going to be on simple harmonic motion. And with simple harmonic motion, we will have an analogy to circular motion. So when I have an object executing a circular orbit, it takes a certain amount of time to complete that circular orbit, and that is called the period. Now, if I want to know how often this object executing a circular orbit passes through a given point, so for instance, how often or how frequently does that purple circle go through the red dot, that is known as the frequency. Okay, so that is the number of times per unit time that purple object goes through the red dot. Okay, so the period is how long does it take for the purple circle to go from the red dot back to the red dot, and the frequency is the number of times per unit time that that occurs. Okay, so that's drawn pictorially up here. We can describe the motion with period. So the time it takes you to go from one point back to the same point, that's the period. And then in a given unit time, the number of orbits we've gone through, right, per that unit time, that's your frequency. And you can see here that that circular motion is analogous to simple harmonic motion, to a spring motion. These are sort of the same, right? If I want to know how long does it take for the purple circle on the spring to go from my laser pointer back to the laser pointer, that is known as the period. If I want to know how many times it's gone through the laser pointer in a unit time, that's known as the frequency. So those are two ways to describe the same thing. So frequency is cycles per unit time. So a cycle could be a rotation, right? It could be an orbit. How many times does it take to orbit? How long does it take to rotate? How long does it take to oscillate? So one of whatever you're repeating, that is known as a cycle. And so however many cycles you have per unit time, that's the frequency. So the SI units are inverse seconds, and we call these hertz, which typically is abbreviated as a capital H followed by a lowercase z. So the period is the time for a single cycle. The SI units here are seconds. So naturally, the frequency is equal to 1 over the period. Or, just by algebra, the period is equal to 1 over the frequency. So these are equations that you should know, and we're going to use these for our simple harmonic motion, or our oscillation, but they're of course also true for circular motion and for rotation. So an example here is you have a clock. So the second hand on a clock, this completes one full cycle, so a circle, a full cycle, in 60 seconds. So the period for the second hand is 60 seconds. If you want to know what the frequency is, that's the number of cycles per second. That's 1 over the period, and so that's 1 over 60 seconds, which is about 0.017 hertz. Okay. Let's conclude with one last question incorporating this last thing that we just learned. So we have a mass that's oscillating up and down on a spring. It completes 10 oscillations in 15 seconds. So the question is, what is the frequency of oscillation? So I'm going to assume that you have pause, thought about it, and come back. So it's 0.67 hertz is the frequency. So remember, one oscillation is one cycle. The time for a single cycle is the period. So the period is the time per number of cycles, right? The frequency is 1 over the period. So our frequency is 1 over the period. This is 1 over 15 seconds per 10 cycles, right? So then that is equal to 10 cycles per 15 seconds, right? You have 10 cycles per 15 seconds, and the definition of frequency is cycles per second. So this is roughly equal to 0.67 inverse seconds, which is 0.67 hertz. Okay, so that concludes this lecture, and that concludes rotational motion. Again, please reach out to me with any questions you have about the class. If you have any questions about the lecture, and I'm sure you do, keep in mind if you do, somebody else does, please send me an email and I will post the question anonymized, so your name will not be there, along with the answer in the Q&A in the Google Doc. If you have any other issues with class, completing things on time because of your personal circumstances, please let me know. I know that right now is a challenge. I'm not assuming that all of you have a consistent, stable access to the internet, but if you don't let me know that that's a problem, I don't know. So do reach out to me so we can come up with accommodations. And whoops, sorry, I just lost my mouse there. Otherwise, please do study. The plan is to have an exam for Monday, March 30th in the evening, and in an email we'll go out with those details. So best of luck, and I will talk to you next time.